Happier now?
All right, so I'm much more happy. Let's try again. Welcome, everyone. I already thought for 5 minutes before the alarm was raised that we have too few people. I'm very glad to actually see the class is still going strong. So let me sort of recap what we just touched a bit over the admin issues. You will only hear from me for the last time today, I promise. So there will be no more lectures from me. However, there will be one more invited lecture in a week on Friday on privacy preserving data mining. My ex-postdoc from Scania now will come to give us a talk. So please attend also in these strong numbers. Other than that, we are going to meet each and every of you on Monday. And Cesar already invited you to fill in the doodle to select your time slot, where we expect a short 15-minute presentation of what you've done so far, which data sets you chose, what experiments you ran, which algorithm you choose to evaluate and test. And then we will discuss it. Then we postponed for a week your milestone report. And milestone report is basically nothing else, just the initial draft of your final report, and that we want you to submit on Monday in a week. And then the big fest will be on 20th, I think, and where everyone, I would like you to come and listen to everyone else's presentations. We'll also send a separate doodle, if not yet, on the slots there. But I would like that you attend everyone's presentation, and then we will have some kind of a voting system where everyone will cast their votes for the most interesting, best, or whatever you would like to evaluate on the project, and then we will give up the prizes at the very end. But the prizes are not the grades, so the grades will be done or extracted by two means. One is the exam that is going to happen, I think, sometime in the beginning of June, and then a week later you will be expected to hand in your final reports, on which also there will be a component on the grade from the report too. And the exam, basically, if you attended the classes and if you at least a little bit understood what I'm saying, then it should not be a big deal. It will be some kind of a bit more involved versions of our Kahoot tries. So maybe it will not be like a yes/no, but a bit more intricate story, and then you would need to choose maybe some options, or maybe explain in a few sentences. But you don't need to read each and every paper that I am putting, on the to-do list. So I mean, don't get scared about that. However, if you cannot follow me what I'm saying, then I expect you open that paper or that book and double check yourselves, okay? So all the material that was on the slides might be in the exam, but I don't require anything extra than that, okay? Good, so any maybe questions about that?
A practice exam or no?
Sorry?
Past exams, would you upload?
This is the first instance of the course.
Well, okay, fine.
An example?
Well, example, I tell you, like Kahoots. So something like I will ask in a sort of style or essence of what I ask in Kahoots, and I don't want you to learn anything by heart. So you don't need to remember any. If there is something that I believe it should be learned by heart, I will put it in a question. I'll say this, and this, and that. What happens then? And then you don't need the computer to extract the answer. All right. Good. So today, I really hope now with this of delay I will finish everything, but we don't have too many slides. So I just want to recap what we've done so far, and in the second, sorry, there was a question there.
So did you have booked this room?
No, yeah, we had a. You came for the exercise session?
An exercise session here, but I mean it's okay now. I just wanted to ask if you had booked this.
No, the thing is that Okay, this is.
They can use our route.
Yeah, we have a SAL-C booked that we didn't use.
Okay. Okay, but it's fine.
Can we?
We had two groups, so the students went to the other one. But
I
just
see.
wanted to know if this was.
Yeah, I'm very.
working or not.
Yeah, it's our fault. But the thing is that we had for the whole semester we had the classes here, and half of the class came here, and I also came and started teaching, and then it was sort of. We just brought the people from the right room to this room because nobody showed up here.
Okay.
But if it's not problem, if you don't have space, please use SAL-C.
No, it's not.
Okay.
Yeah. Okay.
Yeah. Well, okay. Now, hopefully, this class is ours. All right. So yeah, where were we? Yeah. So in the second part of the course, we looked at the sort of topology of the network. So we tried to figure out what it means to have clusters, how to cluster. Last time previously we said if you have some information, some labels, you can then infer the rest of the clusters or the rest of the labels through label propagation. And last time we were thinking how to formally define a cluster, and we said that we could sort of define 4 classes of goodness measures of a cluster, which is internal. For example, if you count the number of edges within the cluster that you say it should be good, so say it's average degree, or it is external when you look at the outgoing edges, say as a ratio cut, or you do both internal and external like in conductance where you take a ratio of the two, or you look global into whole network and compare it to a null model, like what would happen if the edges would appear at random, and that's what we call modularity. And when we looked at that, and later we saw that these things we can extract through one very useful sort of methodology called graph spectral analysis, where when we look at the specific matrices associated with a graph, we can then tell what is the best clusters, say in terms of internal connectivity, for example, average degree, or maybe in terms of conductance and so on. So we know if we look at the spectra of affinity matrix, we can extract the best clusters based on average degree. And by spectra, I mean to look at the matrices eigenvectors and all associate eigenvalues and all associated eigenvectors. Okay, so this is quite a powerful tool if you have maybe not too large matrices so that you can extract eigenvalues and eigenvectors. And just make sure that when you do some experiments, very often it is much cheaper to extract only top k eigenvectors and eigenvalues, or dominant. I mean, in one case could be associated with the biggest eigenvalues, other in Laplacian, for example, the smallest. But the tools you might use, it would be much cheaper to get, say, top 10 eigenvectors than all n eigenvectors. And you don't need all n eigenvectors to do something useful, as we discussed. It's only top k or top 10 or top however, which are important, and the rest you would not use anyway, so don't kill your machines and CPUs with extracting all the spectra and then you just, in a sense, throwing it away. Okay, so that's what we did so far, and what is left is, in a sense, maybe one of the easiest now lectures. This is, as a last lecture, the easiest material, is link prediction. Okay, and link prediction, it's understood, I mean, very easily. The thing is that the networks change over time. So, we have our, say, social graph, our Facebook graph. We have today some friends, tomorrow we meet someone else, and we add a few more links to our graph. Or, God forbid, we actually cut the links. I don't know whether it happens that often in Facebook, but you can also, the network can also both get and lose the links. So, and we would like to predict what happens with the link, or with any pair of nodes in the network, whether they will get the link eventually or not. So in some sense, link prediction is that if you get a snapshot of a network at some time t, would like to predict edges that are added or removed in the subsequent interval from t to some t prime. Okay. And this can be understood like both link prediction or, for example, link completion, since sometimes we might not even be able to observe all the network, because the network itself can be maybe actually decentralized. So there is not even a network in one place. We say our, I don't know, interactions, like what do you see in the metro every day? No, you say if you are in the same wagon in the metro at the same time, you make an edge between two people, for example. It could be construct a graph that way. But there is no such a graph anywhere in the central repository. Facebook maybe doesn't have it yet. Maybe later with some with some advances in when they take over our phones completely, they could extract it. But so far, let's say it's only decentralized, and you can observe maybe only part of that network, but you want to infer later the rest of the links, and that also you can do with these tools of link prediction if you have enough information in this sort of already observed network. And other aspect of the same problem is, for example, to tell how reliable is the link. So if you have a network, for various reasons, say you might be collected some kind of a noisy data, so maybe the link should not be there while you observed it not correctly, so you might want to detect these links. Or sometimes even if the network, the link exists, but it's so weak that it will disappear. So maybe you want to predict that this link will actually be cut. Maybe these people are not very friendly to each other or something like that. So this type of predictions could be sort of transformed into even our understanding from machine learning perspective, and I believe many of you, or maybe all of you, took or are taking in parallel machine learning classes. So for example, this link prediction could be understood as a link existence as a binary classification problem. You just train your ML, some binary classifier, to say whether there is a link or not between any two pairs. Or it could be like regression problem where you want to predict link weight, and that is very, very similar to recommender systems, because you have, say, number of users, you have number of movies. Some users watched some movies and rated them. So with this information, I'd like to predict the rest of the pairs of movies users, and if there's some pair which has a predicts you high value, you would recommend that movie to that user, right? And if it is a low value, then you really, if you're Netflix, try not to bug people and put this movie ahead in their screen. So you want both to avoid the low ratings and maybe put up the good ratings. And of course, you can be even more complex, like for example, you can predict some link type, which could be thought as a multi-class classification problem if there are several types. You have a neutral, friend, and enemy, or positive, negative, and something. So it can be many aspects of that. So now let's go again from the sort of most simple examples and try to figure out where the problem lies. So, okay, so if we have this simple graph, where would we predict a link? No right answer or wrong answer, but let's say here, for no reason whatsoever. Let's say the link should be here, so we predicted link here. But maybe it's correct, maybe it's not. We'll see later whether we can even evaluate that. But what was our chance that we have predicted it correctly? What do you think? So if we want to take this graph, and I say I predict that the link will be here, and I know that for some reason that I know that one link appeared in the next time step, what is my chance that by purely random accident I got that link correctly? Yes?
If you count all of the edges in the complete graph with those nodes, and then divide it by, or no, make the opposite, and then divide by how many edges you have, isn't that like the ratio of like,
So,
yeah.
So maybe what we have to do, we have to see how many possible empty slots we have. right? So in total, how many links there are in the graph? This is our regular formula. I mean, if you have a graph of n nodes, how many possible, let's now talk about n. I mean, this particular case is what is 6, but let's say n. So how many edges there could exist?
30.
N times n minus 1 over 2.
Yeah, so order of n square, and if you want to be precise for a specific undirected case, will be n choose 2 or n times n minus 1 over 2, okay? So, but let's say n square for all practical reasons, so it's a lot, yeah? So n could be a lot, but then n square is even more a lot, okay? Now, how many edges there exist already? Well, we cannot say, but again, I was preaching you the whole, several weeks that we talk about sparse graphs. Real worlds are sparse. So there will be not n square edges of order of n square, but order of n times some constant, or maybe n log n. Okay, so the remaining, the non-existent edges are basically n square minus n times constant, and n square is a dominant factor. So it's still, we have in sparse network cases, we still have order of n square empty slots between any two pairs. So if you just do by pure guess, like a purely at random, we would have only 1 out of n square order chance to guess the node correctly, the edge correctly. So 1 over n square is not a very good odds to play with. So maybe we can do something better. And that's basically the calculation we did, that it's possible edges or order of n square, missing edges n square minus e, and if e is a sparse graph, then it's still order of n square, the dominant factor. Okay. So random guess is order of 1 over n square. So how do we predict a link then? I mean, what would be a suggestion?
Try to complete and make triangles.
Sorry?
Try to make triangles. So like if...
To complete triangles, you mean?
Yeah, like...
Yes.
Yeah, complete triangles.
Yeah, so that's a very, very nice approach. So what your friend says, let's now see if we go now through all our missing edges, see if they complete triangle. That could be a very good approach, actually. We'll see that this is one of the sort of a variant of this is a very, strong predictor. So, but I just want to say that in general, we need to somehow tell that given the specific graph, now for some reason, these two nodes have better proximity scoring than, say, these two nodes, and that's why I chose to predict this link. Okay? So to some extent, I would like to invent a proximity scoring or similarity or whatever. There are many ways to define it. Some function that I could go through every pair of non-existent edge, evaluate the score, and maybe if I am lucky with well defining the score, then I could say that the edge with the top score would be appearing next, and that's my prediction. Or maybe I say the top n. If I take all the scores of all the unobserved edges, order them by the magnitude or rank, and I say I take top n and I predict those. So that could be the sort of the straight away, not very sophisticated technique. And actually, if you tune well a good scoring function for your specific graphs, you could see that they work pretty well. So now, then so of course, this is now the main topic in a sense of today is how to define the score. And already your friend suggested, for example, see if there is if putting a link between V1 and V2 would make a triangle. That could be that means V1 and V2 should have a common neighbor. Right? And maybe if they have two common neighbors, there will be two triangles filled already. So maybe that's even bigger score. So maybe we can make it add up somehow. Okay, so that could be one of the ways. But I would like to start with a very, very naive. As often in this class, we go with the naive approaches and make them more sophisticated, and naive ones just maybe serve for academic purpose, but it's good also for pedagogically to see the trend, how we are going. So most naive ways, we could even say, let's just look, not at even triangles like are sophisticated, just look at the degree of the graph, okay, or the node. If you have high degree and you have high degree, maybe because of that, you will just get a link. And if you have a low degree, maybe you won't get a link. So one way, as you can find in literature called preferential attachment, would be a scoring is just a product of the degrees of two nodes. We don't think about whether they are in the same community or not, whether they have common neighbors or not, just the degree. And you can say do a product, or maybe you can sum up. It's also another way of scoring. You can be a little bit more involved and think about clustering coefficient. Here is only counting triangles locally. So don't count about triangles that will be formed between these two specific nodes. Just say how many triangles are in this area, how many in this area, and maybe it's, again, some product could maybe give us a good guess. Because most of the time, these things are for free for you already. You have it somewhere already computed or stored. So this would be the most naive, but also one of the cheapest ways to score something, because this does not require any specific pre-calculation. Now, if we, and this, unfortunately, while it is very, very cheap, does not take into account even the local topology of the graph. So it does not tell whether these two nodes, Vi and Vj, are in the same neighborhood, or maybe one is in Africa, another one is Australia, in some social Facebook graph. So they maybe have very little chance of being connected, even if maybe they have a very high degrees. So in order to capture that, we would like to use something like your friend suggested, like to see what are the common neighbors, or the common triangles that could be formed. And to some extent would like to capture, as we call the node homophily property, which means that the graphs that appear, because we measure some graph, and this graph somehow grew, and it grew because of certain phenomena that was in the real world, and this real world phenomena often harbor this sort of the
Segregation.
well, both segregation and so the similar nodes tend to get together because birds of the feather flock together, and that's why you often find that if there are two nodes that somehow have lots of other things in common, for example, friends, they're already, by definition, in the local group. They're only 2 hops away, and therefore they're way more likely to get a link than someone who is very far away, even maybe 5 hops away from each other. So we'd like to capture this homophily property, and most sort of, again, the easiest way to do it, just to count the common neighbors. As simple as that. I look at my profile, I look at your profile, I will see how many common friends we have in common. And then I compare myself to the rest of you. And simply, I would say, I will connect to that guy who has the most friends in common with me. And not that I do it on purpose, but this will probably happen in real life, because if we have many friends in common, it means something. It means we are in the same university, or in the same floor, or in the same, football club, or whatnot. So that's one of the basic similarity scoring functions that capture this already homophily. Well, you can do a little bit more complex than that, and it's extend the common neighbors to Jacquard's coefficient, where the numerator is the same as here is the common neighbors, but the denominator you sort of normalize by the union of the neighbors between the two nodes. So meaning that if you have 3 friends in common, might not say much, but if you say we have 3 friends in common out of 5 friends that we have in total, then maybe it's a big score. But if you have 3 friends in common and you are such a guy who just goes around and clicks everyone into Facebook, and in total you and me have 1,000 friends in common, then 3 out of 1,000 is maybe not a big predictor that we'll get together. So maybe, so the Jacquard's coefficient is another way to score it. Now this one, it's called Adamich-Adar score, proposed in the Adamich and Adar paper, is surprisingly very, very effective for certain domains, especially social graphs. And this is also a variant of common neighbor score. So what they do is the following. They sum up something over only the common neighbor. So you see the sum goes over the common neighbors, like here. So if you have 2 nodes, Vi and Vj, and you want to evaluate the score between them, you look first how many common neighbors they have. So they say they have 3 common neighbors. So you now will go over and sum up something over the common neighbors. And the idea is that if you just sum up the common neighbors, maybe it's not enough information sort of to transfer to this similarity function. We might want to look at the degrees of these guys. Now, how do we sum up the degrees? And they suggest to sum up inversely proportional to the degree, meaning that if you have very, very common neighbor, which very, very, very large degree, so maybe it's some kind of Barack Obama style friend who befriends everyone, or and that does not mean that you, this Vi and Vj, have something really in common. So maybe you should not count that node too much, with too much of a hope that it will increase your proximity score. So you dampen it by doing inversely proportional to the degree. And while if you have some common neighbor which has very few neighbors, so if there is a friend who has maybe not 1,000 other friends, but only 5 other friends, and 2 of these friends is Vi and Vj, very likely it's in a small community, so probably it's a good indicator that you will be connected. So if you look at the common neighbors, the fact that they have low degree is good for your scoring function. So you would like to do this inversely proportional to degree, and then again they did not want to completely ignore this high degree node, so they dampened it by a log factor. Okay, so if you have a lot of like 1,000 neighbors or 500 neighbors, log of that would be a similar number, so it will be the same sort of penalty to have very, very large or very, 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 very large number. But in a sense, the score is just a sum of the inverse degrees of all your neighbors with some log factor. Okay, and that is a surprisingly very good predictor. So and these what I covered are very local neighborhood scores. It's sort of this is just a common friend. We did not look any further in the graph. Okay, we just it's of course much better than the previous score, because this was completely oblivious to the topology. Well, a little bit, because you just take a degree, but nothing else. You don't know in which location you are in the graph. Now this gives you already some idea that if you have high score, you should be in the local neighborhood, but you still don't know what is further away. And further away, can you now guess how can you now score, or what would you suggest if you want to take into account not only your immediate neighbors but something further? What would be your suggestion for the scoring function? Because before we just say either we take only the degree. Now the other thing is say let's take a common neighbor, so it's like a 2-hop. Yes?
Something like between a centrality?
Yeah, so we see, so this could be now, between a centrality would mean to measure some paths who come, I mean, between centrality is actually for a specific node, not for the pair, but you can, you know, extract it, say, like I remember what we discussed, the edge between us. That could be one of the ways to look how many paths flow from one part to the other through that edge. So that could be a very good predictor that takes into account the whole topology. So maybe a bit similar one could be just to count the shortest path between these two nodes. Okay, so if there are nodes again Vi and Vj, we see what is the shortest path, and of course the shorter the better. So the shortest would be the common neighbor, the 2 hops away, but maybe they are further away. It would be 3 hops. It's still maybe not bad. It's still better than 5 hops away. So we can score it that way, and this would be called shortest path. Now another variant a bit more involved, it's called cut score, where you say, let's actually look at all the paths from the 2. So we take the shortest path, maybe it's from Vi to Vj there is a common neighbor, but there is also a 3-hop path, and there is another 3-hop path, and there is maybe 4-hop path, and so on. Let's look at all of them, and let's add them up. But we don't want to add up them with the equal weight, because of course the further paths should indicate, you know, less, should be worth less than the short paths. I mean, we are really valued those guys a lot, this path, but not much that very far away path, because maybe it's the link would not be created because of some very strange reason that spans the whole network. So we like to weight it with some betas, and these betas, what the cut score predicts, should be calculated by some beta to the power of path length, and if beta is below from 0 to 1 or below 1, that would be a very nice dampening factor for the very large paths. Okay, and what is other nice thing is that it was shown that if actually you have beta that is less than 1 over the first eigenvalue of this graph, then you can actually calculate that the sum converges. So you can actually calculate the sum on the limit. So that would be like this. You go over all possible paths between these two guys, and then you sum them up with the dampening factor of beta to the power of the path length. And if you remember, we discussed long time ago, in order to calculate that through the adjacency matrix A, you just need to, so adjacency matrix A tells you how many paths from node I to node J exist in one hop, right? This is a adjacency matrix definition. If there is one, that means there is a link, one hop path. If I want to calculate how many paths there exist in 2 hops, what do we do?
Multiply the graph by itself.
Yeah, a square. And a square would give us how many paths there exist from node I to node J in 2 hops. And if you do a cube, it would be the how many 3-hop paths there exist between any 2 nodes. So basically that's what we can put here. We basically sum up a plus a cube square plus a cube plus a to the power of 4 and so on with this dampening factor b to the power of L. And again, we're not going to prove that this can be written in the closed form, and if you can calculate the inverse of this matrix, you get basically the solution of this cut score. So that would be the identity matrix minus A multiplied by this coefficient, inverse of it, minus identity matrix. So if you have, if your graph is not too large that you can calculate the inverse, you can very quickly calculate the cut score between any 2 nodes. So that's a sort of a path-based similarity measure. And there are more. For example, you could think of, I will let's say start a random walk from node Vi and measure how many hops it takes until it hits the Vj. So now let's say I issue one random walk, it reached in 2 hops. I issue another random walk, it reached maybe in 4 hops. Another one in another 3 hops, and then so on. I made some number of 1,000 random walks, make an average, and that will be my hitting time empirically observed between the node Vi and Vj, and I say that the score, the proximity score, would be that average. And of course, you could now notice that this is very similar to label propagation with absorbing states. Again, you can rewrite it in the, if you want, in the matrix terms, similar what we discussed with label propagation, but this is the generic idea. So this score would call hitting time. If you, for directed graphs, sometimes you would have that going from Vi to Vj is sort of more likely that the other way around if there is, say some kind of directionality involved. So you might want to compute both hitting time from I to j and from j to I, and maybe sum them up together. Or there is even sort of updated version. What they note is that if you have a graph with a very skewed degree distribution, and again, as we discussed in the previous lectures, or especially one of the first lectures, that real-world graphs exhibit power law degree distribution. And if it is power law degree distribution, then of course some of the nodes will have very large degree. And if you remember for our page rank discussion, the large degree would give you, probably much larger, page rank score. In a sense, the station distribution of the random walk would tend to go to these higher degree nodes, and that's why you might want to normalize that hitting time or commute time calculation with the station distribution of the basically of the random walk in that graph. So that's another thing. And in general, there are many page rank based variants. We already discussed some, like a sim rank in our class, where we're comparing the pictures trees to some the objects to the pictures that we're depicting, or something else in a bipartite graph, where you can use this personalized or the rooted page rank score to calculate the similarity between a specific node and anyone else in the graph. And if you have a high score and still don't have an edge, it could be a very good indicator that the edge will appear. So this would be a page rank based variance. There are many of them, so I will not even go over them. I will give you a link to a paper which tries to evaluate a lot of them, and some of the graphs we will see from there. So these are, you can call it a path based score, the random walker based scores. Now another way to look at the scoring is, again, looking at the one way to the linear algebra and the graph spectra. So if you remember, we discussed that how we cluster graphs. We take the eigendecomposition of the graph, we take the dominant eigenvectors, then we describe a coordinate in our new low dimensional space of a node as a coordinate involving these k or selected low dimensional eigenvectors, and this coordinate gives us the interpretability how one node is close to another node, because every node gets this coordinate in low dimensional space, and just by looking, say, at again some cosine similarity, we can say the score between any two nodes. And the high score would be if they're in the same cluster. If they're in the same cluster, it's more likely they will get the link together. So this low rank, as we call approximation, gives us also a very good idea whether the link will appear or not. I just want to recap so that you, maybe what I just said still does not sink down. So we start with some matrix A, or any other matrix actually describing the graph, but again, A is the adjacency matrix, right? So or you can, could be weighted, unweighted, doesn't matter, but what's important that if it's 0, the link does not exist. If it is non-zero, 1 or something more, that means either the link exists or the link is very heavy. So the more the merrier. So we have some, say, ones somewhere. And what we can do, as we saw here, we can decompose that matrix into now three matrices, which would be basically X the same edges transpose. So basically here we have some vectors. Here are the same vectors, just laying down. And this matrix is a diagonal matrix. Okay, this is 0, 0, there are something here. Okay, and this we call, these are the singular value matrix. So this is nothing else as here are sorted eigenvalues from largest to lowest. Okay, and this eigenvalue has associated eigenvector here, and then here as well. And then that one has associated vector here and here as well. Okay, and now what we know is that they go from large to low. Okay, so what it means is that if we multiply these three matrices together, we get exactly A. Okay, but now if we want to sort of reduce dimensionality without losing much of information here, so sort of if we want to approximate, okay, nearly the initial values, maybe if it was 1 it will be 0.99, if it was 0 maybe it will be 0.001, so nearly the same. If you now look at if you now get this is equal, and if you calculate some approximate the difference of the two, if you make a difference and say the sum up the errors would be very small. So this you can do with the following way. You can argue the following way. You can say that this matrix, again, can be decomposed into many. Okay, let's put it that way. I want to understand this, but this is quite important. I can write this thing in the following way. I can take the first eigenvector, take the first eigenvalue, and the first eigenvector, plus second eigenvector. So this I took first here. Now I took the second here. I take second eigenvalue here and second eigenvector there, and so on. Third eigenvector, third eigenvalue, okay, and so on. So now what I have is the what is called the, not a dot product, the outer product of two vectors. It gives a matrix plus another matrix plus another matrix and so on. Now the thing is that the eigenvalues, eigenvectors are always of the same length. So they're the same sort of, on average, sort of size. So they're actually not only the same, they're orthonormal. They are orthogonal to each other, but maybe orthogonality is not very important in this case. But what is important that they're of the same, they're the same length. And if they're the same length, the outer product that they do between these two values will be more or less of the same size. So if you were ignoring eigenvalues, and if you sum up all of these components, each of the components will contribute more or less the same amount, so we wouldn't want to remove any of them. But the trick is that while this outer product is of the same size, we always reweight it by the eigenvalue. And by sort of convention is that we say that the dominant eigenvalue is here, so this is the largest, and then they go down and down and down. So the components that you sum up will start losing the influence to the final A. Okay? And what we say that, and there is sort of a rule, if you take the overall weight of this, a trace of this guy, it's actually usually take the squares of that, and take an 80% of the volume, and say 80% of the volume is here, the rest is just sort of crap, you can actually remove that from the calculation, these guys, without losing much. Because there were so few values, there were so little contribution, and the most contribution happened here because they were scaled by a very big eigenvalues. So in the end, you still end up with more or less the same A. So what it means that you can rewrite this guy into now some much more narrow x, which would be like, so now it would be k, n times k. Here it was n times n, n times n, n times n. Here is now n times k, where k is only the sort of, they say, 80% of the volume. And maybe it will be, and again, depending where the eigengap is, because think, this is if I order this by some, by the size, this will indicate that there will be a drop somewhere if the graph is clustered, and that will indicate a gap, meaning that I only take things up to here, below I don't care. So what I would do, I would now end up with a new decomposition that takes into account only k dominant eigenvalues that are biggest and associated eigenvectors that matter, because the rest do not matter. These do not matter. Okay? Because the eigenvalues were very little, or maybe even zeros. If it's actually if it's disconnected graph, it could be even. So what it means that now, instead of having a coordinate of I, some large dimensional space, like n million, yeah? So 0, 0, 1, 0, 0, 1. Now I transform it to another coordinate, which is much lower dimensional space, just k. And k, as we saw, could be as small as, just little, like few dozens. Okay? And these now give me a new interpretation of what a node is. And then if I now make say this is now three-dimensional space, if I take K3, I will have nodes that have maybe three, if the graph had three clusters, they will be clustered in three very nicely pushed away locations by these eigenvalues, where the nodes of the same cluster will have very, very similar coordinates. And if you do a dot product between any two I and j, this dot product is sort of a version of cosine similarity. It would give you a very good indication that if you have a very small angle, that they will be they might get a link together if they don't have the link so far. So this is called the low rank approximation approach. It's basically the same like what we discussed for graph spectral clustering. It's just that instead of just clustering, we actually take this, we map the graph into low dimensional space. We assign the ID or the coordinate based on these k eigenvectors to every node, and then some kind of a, say, a version of a dot product or similarity between these two IDs in this space would give us a similarity score that we can later use for link prediction. Okay. And this could be extended to actually not even a square matrix, but any matrix, and you can think about movies and users that does not need to be squared, and that could also be decomposed in a similar way, and we call it singular value decomposition. So this is a very powerful tool that you might use in many, many aspects. Okay, and here is in one of the papers they show they had some kind of a 5 or something the data sets. I think they were all social network based, and they did this singular value decomposition, and here are how many dimensions they took. So as we say, we took k here, and here they measured if they took only one, that means only the dominant eigenvector. If they took 4, let's say the 4 of them, or 16, or 256, or 2024, and this is the goodness of the prediction somehow. This is the relative performance versus the random prediction. So random is what we said, 1 over n squared, which is the drop a edge at random, and here was if you compare it to random prediction, so the more the better, and you could see that the best predictions happen when you don't have you don't need to go all the way towards end. You actually have to stop somewhere. There's a sweet spot, and the sweet spot is like around 64 64 dimensions. That means they mapped into 64-dimension space. Except there was one strange outlier where the best predictions were in one-dimensional space. So meaning maybe there was some graph where it was really so simple that the phenomena happened only on one dimension. And again, this is just a message to you. This is not that now you have to always use 64 no matter what. It depends on the graph. So maybe you need to try several and see where the bump exists if you want to go that way. Yes?
Two questions. The first question is, why does, I mean, I understand that it might taper off, but why is the predictions actually getting worse? Because shouldn't it just be getting more accurate with every, I mean, not by much, but still more accurate with every additional...
No, because the thing is that if you are super accurate, you predict 0 between two non-existing. Because you see, here, if you're very accurate, you reconstruct A.
Mm-hmm.
A cell between two nodes that do not have link is 0. So you'll predict 0.
So in other words, you won't predict anything.
Yeah, so you want to have this sort of a place where you predict the phenomena of the clusters, but don't go into this, the specularities where you actually make sure you do not see the link there. So in a sense, I want to not to see the links between the far away sort of clusters, not between specific even location within a specific cluster, because that's what you are forced when you take into account all the components.
Okay.
So, and that is the point. So, and usually the thing is that if the phenomena that is sort of happens in some kind of 3-4 ways, then probably you need 3-4 dimensions. If you select friends based on geography and I don't know your hobbies and occupation and so on, then that means that's how many components you might need, and maybe for every this phenomena you might need few dimensions, like geography would need 2 maybe, and then for hobbies maybe a few more. So in the end you don't need much compared to the size of the network, which can be hundreds of thousands. So the phenomena can be encoded very well in a few dimensions, but if you force more and more, then you will sort of overtrain and will predict exactly the input, which you don't want to do that.
The second question I have is, does this basically mean that there are about 64 clusters in the data sets?
No.
No, it does not.
That can not necessarily, I mean, that sort of means that there are well, I cannot say 64 phenomena, but the phenomena that make the graph can be described in 64 dimensions.
Okay.
So let's say like this, if you could think it that way, if you had only geography-based phenomena, you would need 2 dimensions. Because 2 dimensions sort of would describe well the geography.
Okay.
Right, and then but I mean, the world is much more complex than that, so yeah, so that's... And then just to finish it up before I give you a short break, I'm so sorry, I really want to finish everything today. So I'm eating up with your free time. So here is the, actually now there's this paper that took into account most of this, what we discussed, the similarity measures. They took several, the real world networks, and let's say how these similarity measures compare for link prediction in different sort of ways. And the baseline, they say, let's do the random just prediction, which is of course the most naive and silly prediction. And of course all of them did better. You can see this is the, for example, hitting time, this is SIMRank, this is Jacquard, this is CATS clustering, and that one is Adam each other. That's why I said this is a very good predictor. So you could see they were all, doing much better than the random predictor, but maybe this is not a big standard. So let's say if the standard is common neighbors, that we said this is almost for free. Just look at the common neighbors, nothing more. And as a matter of fact, if you look at only the common neighbors for social graphs, this is the social graph-based data sets, you're already doing very well. And some of the predictors are even doing worse than that. So, you might, go for some kind of hitting time or SIMRank that is very hard to calculate. I mean, much more, you need to involve maybe, some kind of power iteration or, other random walks, while the common neighbors is nearly for free and you're still doing worse. So the only the score that was doing very well is this Adamich Adar, which again it's a very cheap score. You just need to look at the common neighbor degrees and you can calculate that, and it still gave a very large output. And actually I think there were two papers with this sort of, one is extended version, and the extended version they added this low rank approximation, which also gave quite good scores. Yeah, so basically this is the simple way to do it, and you can also complicate further and then take your knowledge from the machine learning class that you took maybe or taking now and just treat all these scores as the features for your ML block. You know, you just, and then you generate the features, you take your favorite approach, whatever the logistic regression, SVM, decision trees, whatnot, and then train, test it, and put into production. So then the question is what kind of features you can do, and of course you can take only these topological, the structural features that we discussed before, say, and also you should not make like too many correlated features as an input, because again what we showed before, like many of them are variants of a page rank. So maybe you have to be careful with that, because as you know, you might have issues if you have too many correlated features in solving your ML problems. But that's for ML class. I'm just giving you sort of the connection here. But as a matter of fact, you can even upgrade it and take not only the topology of the graph, you can take something more for your ML and maybe some kind of content. And if you are, say, want to analyze the collaboration graph between the scientists, you can take as a feature, for example, paper domain, if it is in physics or music or chemistry or whatnot. So it of course can be much harder, because suddenly you can realize that you have to evaluate very large of this number of say possible pairs. Because as we said, most of the pairs do not exist in the real graphs, so you have to go through n square of negative examples and sort of evaluate them while training your model. But the biggest issue will be that the class will likely be very imbalanced, because, as we said, graphs are sparse. So out of all possible sort of n square edges, you observe only very little order of n existing edges. So your classifier, if you're not careful, can just easily say, I just predict that no edges will appear. And if you do again a very simple evaluation score, it will be doing quite well in most of the cases. So you have to make sure how you choose this sort of how you train your classifier, and you might want to do basically a downsampling for this negative example, so you don't show too many non-existing edges, and you upsample these positive examples, maybe show a bit more these existing edges. So you have to be careful with that if you're going to work on link prediction using ML. And of course, you have to double check if your features have these discriminative abilities. So for example, here are the couple of features. This is what is this? This is the cut score. This is a graph distance score. This is some other score. I'm not sure. But the upper one always says the scores when the edge exists, and this edge one does not exist. And you can see here it's a very clear cut, meaning that the score is above 4 when edge exists, and below 4 when edge does not exist. So it's a very good discriminative feature. While here it's so-so, when edge does not exist, you will always have high, but when edge exists, you might have both low and high. So ML can have a bigger issue. And here it's even more confused. So you have to look at this as well while you do it. And then the lastly is how to evaluate your whatever you trained your model. Because, and maybe that's also important for your project, is that whatever you do, at the end you have to show that this was worth doing it. You have to have a ground truth and somehow evaluate whatever you propose, let's say this is now 10% better or 10% worse. Doesn't matter. I mean, this could be a negative approach, but still it has to be evaluated. And you evaluate, basically, you take maybe out of the whole graph, you hide, say, 20% of nodes. You train your model on this, on the 80% of the nodes, and then evaluate on the remaining 20 when you say, now I have my good understanding, good model, and I'll be able to predict. And I'll try to predict these edges that you hit before. Or if you had a time evolution, because here if it was no time, if everything is only one snapshot. But if you have snapshots in the graph, what you can do, you can say, I take some kind of a window. I take a graph that exists in this, say, 1, 2, 3, 4, 5, 6 time slots. I basically train, I use labels, or I show the graph what should appear in the next time slot, and I train a model, and then I test it on the sort of by shifting the time slot. So then I say this is my input, and I'll see if I'll predict the rest of the edges that appear in that time slot. So this is how you're going to do, and here you can see, I will put some link to a paper that is proposing that technique. And then the lastly is evaluation measures. And maybe you already heard in the even other context. The most default one is basically precision, is how many selected items are relevant. And this I took from Wikipedia, it's easy to understand. So say, if this is the Oracle view, and you know that there are, this is the world, and these are the true negatives, and these are true positives. So our best guess would be only the left part of the graph, but of course it's not perfect, so maybe we only output this part, and now how bad we are with that. So in one sense, we say precision is basically out of this what we output, what's the fraction of the good ones. So the green part versus the bubble. Okay, and that is our precision. How many selected items are relevant? You could also say what is the recall. That means we could have very high precision, but we did not really output most of the good things. We did not output bad things, but most of the things we missed. So meaning, what is the recall out of this green crescent, what is compared to overall green true values. So this is the recall. The opposite of that is false alarm ratio, false positive rate, meaning that this false positives over compared to all the all the negatives, basically false positives and true negatives. And then you can see how many, what's the fraction of the bad guys we outputted, or the wrong guys. And often you can, have a high precision but low recall, and this is the, you have to sort of balance between the two. And one of the sort of balance measure is F measure. And F measure is basically the fraction between the product of precision and recall over the sum of the precision and recall. So you can balance. The F measure would tell you whether you are good somehow in both. Also, there is I forgot this. There is an accuracy. Is the true positives plus true negatives. So that's what you should. What you should have guessed. What you should have not guessed. Over all things. That's the overall accuracy. So you also want to increase that. And another thing, have you heard of the area under the ROC curve? So this is, in a sense, here if you measure many instances of your classifier, for example, if you take now order all of the non-existing edges based on some similarity measure, that your favorite one, but then you have to say, when I put the line, should I take the top one, or I should say 0.75 or something? So this line could be drawn anywhere, right? So if you're very, 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 how to say, safe, your threshold will be very high, and then you will not predict anything. So you're basically your bubble will be so small it will not take into account any dot. So your precision will be basically 0 because this is the nothing to even didn't output anything. But your false positive rate will also be 0. So that's good. You want to be false positive rate also good. So you would be somewhere if you have a. I will. So if it is, you measure 2 dimensions, false positive rate and true positive rate. So if you are very careful, everything will be 0. Now if you say I'm not careful, I actually whatever, I predict everything. So my threshold is very low. If you have a bit positive score, I just predict. So then you'll predict everything. So your basically true positive rate will be very high, because you basically recall is great. You predicted all of the good ones, but also you raised false alarm for everyone. So then you are here. So these are both sort of useless things. But then in between, if you tune your threshold, you could start measuring something. Yeah. And the best thing is that if you measure, of course, the best would be here, that you predict only the left part, so meaning that the true positive rate is very high while you did not raise a single alarm. So the best one would be somewhere here, but in real life it will be something like that. And then you calculate this area under the curve, and the more towards that side is, the better your method is. So that's how you interpret area under the curve. And in real life, it's actually not that bad. I mean, you can think that this is now too complicated. Actually, prediction results do not need to be that good. I mean, don't cite me on that. This is sort of a generic thing. For example, recall does not have to be good because people are not upset if they do not know what they didn't get. I mean, they might be very cool things that could have been shown by Netflix or Google, but as long as I am showed things that I liked, I don't know what I did not get very cool, so I'm not upset. I would be upset if I'm shown something bad. And even with the bad, which is precision, also might not be that sort of tragic, because if you show me a list, and out of this list, top few are still good enough, I don't even care about the rest. So so these things are sort of negotiable. Okay. And this I'll put some relevant papers that you can look at. So let's take a 5-minute break. We'll do later Kahoot, and then the last small section on graph representation learning. I'm very sorry, I'm somehow very slow these days. But so 5 minutes just to go to the bathroom if needed, and then we come back and we continue.